percent composition? Percent composition is a very useful tool out in the industrial world. It tells us a lot about what is the makeup of a particular item. For example, you buy soup. What percent of the soup is water? What percent of the soup is beans? What percent of the soup is the ham, right? And there's lots of ways we can do that. And it basically boils down to this. Percent composition is basically what percentage or fraction of the total is made up by each component. And the generic formula is percent composition is the part that you're looking for divided by the whole times 100%. Now for chemical compound, we're going to deal in mass. So the percent composition by mass is just the following. It's just the mass of the component in the compound divided by the mass of the compound times 100%. Remember, this is going to represent my part and this is my whole, right? Now, why do we care about this as chemists? Well, suppose you're a forensic scientist and you're at a crime scene and you notice that there's rust, and that rust is going to be a key contribution to solving the crime. But we don't know what the rust is or the iron oxide is. We just know it's iron oxide, right? We take the iron oxide back to the lab and we analyze it for how much iron is in the sample and how much oxygen is in the sample. And we can do that with all types of modern equipment. Now, we can compare that analysis to the percent composition of FeO, which is iron 2 oxide, versus iron 3 oxide, which is Fe2O3. And if we can calculate what percent composition is of this for each element and percent composition of this for each element is, and we can then compare that to our analysis and determine whether or not it's indeed iron 2 oxide or iron 3 oxide, and therefore we can solve the crime. So let's go back to the lab that we did with the Oreo cookies. Now we can use percent composition in there, and we did calculate it for each cookie of what the percent composition of each component that made up the cookie. Both cookies are made up of the same basic ingredients. We have the cookie component, and there's my cookie component, and cream component. The difference is in the double stuff, it appears that we have about twice as much cream as we do in the original cookie. And we understand that that may or may not be exactly true. There might not be exactly double the stuff, but the intent and purpose of the cookie maker was that we're going to put about twice as much cream here as we do here. And we could do an analysis to see if that is really true. Now, by looking at these cookies, you already know that they're going to have a different composition, even though they're made up of the same basic 3 ingredients, because one has more cream than the other. So by definition, we should have a different composition of this cookie than we do of this cookie. And we do. And we're going to try now to extend that into how does it work for a compound. So here are the cookies again, and we're going to use the cookies to model 2 compounds with the same basic elements but in different ratios. So my first model is going to be hydrogen peroxide right here, H2O2. So I have 2 oxygens and 2 hydrogens. And then this one here, it's a standard water, 2 hydrogens and 1 oxygen. So now look what they represent. If we're going to model this with the cookies, we can say that each cookie has 2 chocolate cookies. And so we're going to say, and each compound has 2 hydrogens. So let's say that each hydrogen is represented by the cookie. So we have 1 here and 1 here, and 1 here and 1 here. And that makes sense. You can see that right away. And then let's say now the oxygen in the compound is going to be represented by the cream layer right here, right? And in my double stuff, which is this cookie here, I'm going to say that we have twice as much cream. Therefore, if I say have twice as much cream, just like hydrogen peroxide has twice as much oxygen, we can put that right in here. So now we have the breakdown of the model based on the cookies, right? So how did we find the percent mass of each one of the materials in the cookie? We did that by weighing the whole cookie and then weighing each component of the cookie, the two cookie halves and then the cream layer. And we got a mass of each one of these, and then we just did the formula where we took the total mass of the cookie as our total and then divided that into the mass of each component and multiplied that by 100% to get the percent by mass of each one of the components. And when we did that, we saw that the mass of each one of these components in this cookie were going to be different than this cookie. Now we can do the same thing with a compound, except we don't have an easy way to measure each one of the atoms. So what can we use so we know we can easily measure that represents the same number of particles, and that would be the mole, or a molar mass. So if we represent the total mass of the compound with the molar mass of the compound for our formula, then if we divide the molar mass into the masses of each one of the components, we should be able to get a percent composition of each one of the components. So let's look at that real quick on the next line, right, on the next slide. All we're going to do now is we're going to find the individual masses of each component, molar mass, divide that by the total molar mass of the compound. Remember, this is the sum of all the molar masses, and then divide and multiply by 100%. And that will give us the percent composition of each one of the ingredients in the compound, or each one of the elements in the compound. Alright, so now let's look at an example with some real numbers. What is the percent composition of potassium chloride for each element? Now remember, step one is to determine the mass of each element in the compound using the element's molar mass. I can look that right up on the periodic table. So I get 39 grams per mole for potassium and 35.5 gram moles for chlorine. Now we're going to, as we do for any molar mass of a compound, we're going to add them up, and we get 74.5 grams per mole. Now remember that this is going to represent our total mass in our formula. Okay. Now we go back to the individual masses that each element contributed to get our formula. So remember, this is my total mass, and we can put that right here. And this is our individual masses from each one of the compounds to get the total mass. And when we do that calculation, the potassium is 39 grams out of the 74, so we get about 52.3%. And the chlorine is 35 grams per mole divided by 74.5 grams per mole. That gives me 47%. Now these have to add up to 100% because there's only two constituents in there. And it does. So that's a sample calculation for that. So example 2 is magnesium hydroxide. Now the nice thing about magnesium hydroxide is that each molecular formula has, not only does it have 3 individual types of atoms, that 2 of those atoms right here, oxygen and hydrogen, come multiple times in the compound. So again, we're going to use this to our advantage. So when we determine the mass of each element in the compound using the element's molar mass, we have to make sure that we multiply the molar mass times the number of times that element appears in the compound. In this case, for oxygen and hydrogen, it's twice. And then we add all these up, and we get the molar mass of the total compound, and that's listed right here, right? All we've done is we've added all these individual masses up to get this. Now, once we have this, we're going to go back and look at each contribution of each element's mass to that total mass there. So when we look at magnesium, again, magnesium, the molar mass of magnesium is 24.3. There's only one of those, so we're going to break that down here. And remember, the molar mass of the total compound is down here, and when we do that mathematical equation, 24.3 divided by 58.3 grams per mole times 100%, we get the percent composition of magnesium in the total compound is 41.7%. And then you could do the same thing for the other two elements. We'll just do one more here. For oxygen right here, remember we have to use the 32 because there are 32 grams of oxygen by mass in 1 molecule of MgOH2, which is magnesium hydroxide. Again, 58.3 goes right here because that's the total, and when we do that math, we get all 54.9%. And then to check it, we add all these masses up to make sure we get 100%. So here's where you're going to try it. Again, I give you two compounds. You want to know the percent composition of each element in each one of the compounds, right? So again, you're going to need to know what the molar masses of each element are. You're going to have to find out the molar mass of the compound is, and then use those two pieces of information for each element to calculate the percent composition of that element. So you're going to stop the video, work the problem, then restart the video when you want the answers. So stop the video now. Here are the answers. I've calculated the molar mass of sodium hydroxide here and the molar mass of ammonium sulfate here. Using those numbers and the numbers for each individual element, you should have gotten these numbers, right? If you didn't get these first, you might have that's where your error is over here. So check these first, make sure those are correct, and then if those are correct, make sure you did the math over here right. So if you're still having problems with this by the end of this lesson, you want to come find me and ask questions in class.